So, I'm going to talk now about we're going to focus on 4 plus 2, which 4 atoms plus 2 atoms, or 4 electrons plus, in this case it's 4 electrons plus 2 electrons. In fact, 4 pi electrons plus 2 pi electrons in terms of cycloadditions. There are other types of cycloadditions which are not 4 plus 2, but I'm focusing just on this group, and in particular, amongst them on the Diels-Alder reaction, which is 4 carbon atoms plus 2 carbon atoms to make a 6-membered ring, or as we will see, 4 pi electrons plus 2 pi electrons going into the reaction. Because of its, and the reason I'm focusing on that is because of its importance, the Diels-Alder reaction, in organic synthesis. I want to look at, we looked at why the reaction works in frontier orbital terms, but that doesn't tell you what you can do with it. Doesn't tell you about the reactivity of the components, so it works, but which ones will go faster than which other ones will work better than which other ones. It doesn't tell you about regiochemistry. The specimen Diels-Alder reaction I showed was just butadiene plus ethene. In fact, that reaction doesn't go very well. So what about if you have a substituent, do the two come together like that or like that? Which ends are joining to which end of the other component? That's regiochemistry. And stereochemistry, because you're forming some new sigma bonds, you're forming some new saturated sp3 centers, so there will be some stereochemistry, and we need to think about stereochemistry in the starting materials, how that translates to stereochemistry in the products. And that's these things about reactivity, regiochemistry, and stereochemistry are going to be vital for thinking about applications in synthesis. So that's what this next session is going to be about. Whoops, that went twice. Okay, so it's called the Diels-Alder reaction because of these two gentlemen. This is Otto Diels, this is Kurt Alder. He was the PhD supervisor, he was the PhD student, who then went on Alder to do much work on his own to develop the reaction after his PhD. As you can see, he was significantly younger than Diels. That shouldn't be an equal sign, obviously, a mistake. The Nobel Prize was given to these two in 1950 for this reaction. In other words, by then recognizing its importance in making 6-membered rings, in making them with a defined regiochemistry and stereochemistry. It's a thermal reaction. In other words, it just needs heat. It doesn't need any other reagents. And I should have emphasized about pericyclic reactions. We don't need other reagents, generally speaking. Sometimes we can catalyze the reactions, but mostly it's just you bring two components together, or you have one component cyclizing on its own or something like that. There's no added reagents, except maybe for catalysis to make it go a bit faster. It's concerted, so it falls into the pericyclic bracket, pericyclic group. It's a cycloaddition, so it's forming 2 new sigma bonds there and there. It has a cyclic array of pi electrons, reorganization of electrons in the transition state, so that's why I'm drawing it here. And it's 4 plus 2, well, it's 4 atoms plus 2 atoms, but here I've said it's 4 pi, that's 2 pi bonds here, a diene, that's 4 pi electrons involved, and 2 pi in the alkene. It's a 6-electron cycloaddition process in which a diene, a 4 pi system, combines with a 2 pi system or an alkene. In this context, that's the alkene has been called a dienophile, meaning it's just something that loves dienes, something that wants to react with dienes. So that word is quite specific to this kind of reaction. To produce a 6-membered ring, and the significance there is forming a new ring. So 2 bonds in one go. So one of the early examples of forming complexity quite rapidly in a synthetic sequence. The geometry, and this is something we must explain as we go along here, the geometry of both the starting pieces is preserved in the product. So the reaction is stereospecific. An obvious example of that is if 2 groups obviously on the dienophile, the alkene, the 2-pi component, you could have substituents at either end, and if they start out as cis or Z in the starting material, they remain cis in the cyclohexene product. And if they start out as trans or Z, they remain trans in the product, and so on. Why does this reaction go? Why is it favorable? Because we're breaking 2 pi bonds and making 2 sigma bonds, and that corresponds to an exothermicity of about 167 kilojoules per mole, or 40 kilocals per mole. So it's the sacrificing 2 pi bonds to make 2 sigma bonds is energetically favorable. So that's a little bit of the background and sort of general statements about the Diels-Alder reaction. A little bit more here. The 6-membered transition state for the reaction resembles a folded cyclohexane. So it's like a sort of boat conformation. So I can't really see it in these drawings, but if you were to imagine the bonds being formed here, diene and dienophile, or here as well, if you imagine the shape of that, it's a bit like a boat conformation of a cyclohexane. Well, I say figure below, it's the figure alongside actually, shows the progress of the reaction with line structures and with orbitals. So that's the line structures, and we've got essentially 2 planar components coming together, one on top of the other. So that's where the reaction being suprafacial on both components, I referred to in the first session, where that comes from. And the bonds are going to be formed from here to here, and from here to here. Or in the orbital sense, here is our HOMO. I've drawn just the HOMO diene, LUMO dienophile, but as I showed last session, you could reverse that as long as you have one is the HOMO, one is the LUMO. So one is a filled orbital and one is empty. So here is the HOMO of the diene. So it looks like, in terms of phases of the orbitals, looks like 2 isolated pi bonds. Here is the LUMO, the unoccupied orbital, pi orbital of the alkene. It's the pi antibonding or pi star orbital. Both components react suprafacially because that's the easiest way for them to approach geometrically. So the 2 planar molecules are coming together, one over the other. Not quite on top, we'll see how that works, but one over the other. And again, drawing the orbitals again, you'll see that we get an allowed, or positive, constructive, I think was the word I used in the previous set of slides, overlap to form each bond. So that's looking good. So the frontier orbital theory is an easy pictorial way of saying this should work. It doesn't tell you how well it will work, it doesn't tell you what the stereochemistry is going to be, or the regiochemistry. Regiochemistry doesn't tell you which end of the alkene is going to join to which end of the diene. Can we predict that? And the answer is yes. So the p orbitals of the pi bonds become the sigma bonds of the product. So you're going to get an end-on overlap here and an end-on overlap there, which in each case will make a sigma bond. So how can we have a really effective Diels-Alder reaction? The prototype Diels-Alder reaction does not really work very well. You need to heat it very hot, you need to leave it for quite a long time, and you need to do it under pressure, because we're forming two molecules into one, so pressure will help push that reaction. So that's not a reaction you'd want to do in the lab every day. If you put, on the other hand, if you put an electron EDG, electron donating group on the diene, and an EWG, an electron withdrawing group on the dienophile. I apologize for using these abbreviations, but that's a donor group and that's a withdrawing group. So a donor group, like a methoxy group, where you have lone pair of electrons that can donate in through resonance delocalization into the diene, and a withdrawing group here, a carbonyl that can both inductively and through resonance withdraw from the alkene. This reaction is an effective reaction. It's now going at just 100 degrees in a couple of hours and no need for high pressure. So clearly this statement is true, greatly accelerated by a donor group on the diene and a withdrawing group on the dienophile. So here's simple butadiene, no substituent, and a withdrawing group on the dienophile, 150 for half an hour. So that's pretty effective. Here's a version of the diene with a donor group on, but not at the terminus, at an internal position. Again, 120 degrees, 6 hours, a little bit slower than this one, but which is isomeric with, but still a feasible reaction. And notice in these that the regiochemistry here is such that these two substituents end up in, if that was a benzene ring, you call them ortho to each other. So I've put ortho in inverted commas here to indicate that these are next door, or 1,2 to each other. If the substituent on the diene is at an internal position, then you get an arrangement that is effectively like para in a benzene ring. So ortho and para products predominate. We need obviously to explain that, but it does mean that we get some regiochemistry, because otherwise, if this component here would go either this way up or inverted the other way up with the aldehyde substituent at the bottom, you'd get two different products. But there is a preference. Ortho and para products predominate, as long as you know what we mean by ortho and para in this context. Lewis acids catalyze the reaction. So this reaction, you look at this, cyclopentadiene with methyl propenoate, methyl acrylate. With aluminium chloride as the Lewis acid catalyst, it goes at minus 78 degrees. So very much accelerated, and we'll see about why that may happen as we go through this session. The Lewis acid is complexing as it happens to the carbonyl oxygen of the substituent on the dienophile. And here's a straight comparison example. This pentadiene and this methyl acrylate again. Without catalysis, you get 90% of what I'm calling the ortho product and 10% of where the dienophile has gone the other way up. With aluminium chloride, the regio, as well as going faster, which I'm not indicating here, but it also affects the ratio. So it improves the amount of the ortho or 1,2 product in comparison to the meta or 1,3 product. So there's a number of things there that we need. These are experimental findings, but we need to see if we can find orbital descriptions for these. Okay, this is a fairly complex slide, but let's see if I can pick the main pieces out of this. Increased rate of reaction with electron withdrawing group on the dienophile. An electron withdrawing group, which we'll call a Z substituent on the dienophile, it lowers the energy of all the orbitals, but therefore of the LUMO in particular. Okay, so the best, if you lower the energy of the LUMO of one component, then the best energy, or the smallest HOMO-LUMO gap, is going to be with the HOMO of the diene matching the LUMO of the dienophile, rather than the other way round. Because if we're bringing down the LUMO, then it's going to come closer to the HOMO of the diene. And catalysis by Lewis acids arise from even further lowering of that LUMO. So let's see what we're doing here. How do we try to account for a withdrawing substituent like a carbonyl on a dienophile, an alkene? So this is effectively our Z substituent, our withdrawing component. Well, we think about that in terms of the alternative resonance form, which would look like an allyl cation. So it's the influence of what is the influence on the two reacting centers, the alkene centers, of having a carbon next door that is electron deficient because it's part of a carbonyl group. So the way we do that is imagine how having that allyl cation would modify the electron densities, the pi electron densities at the alkene centers. So this would be the alkene with no substituent. HOMO, LUMO, occupied, unoccupied. Okay, now let's imagine that that is really, because it's got a substituent on, our model for it is to think of it as an allyl cation. Well, the allyl cation has 3 orbitals, and a complete a bonding, a non-bonding, which has no electron density at the middle, and an anti-bonding situation. And what that means is that the two pi electrons that are in the alkene are being slightly stabilized because of this next door electron deficient carbon. So that the orbitals are now, the electrons are now here rather than there. But then look at the LUMO, that's been rather dramatically lowered in energy. So if we're interacting with the HOMO of the diene, here's butadiene, we're not doing anything to that, we just leave it as butadiene. Instead of it being an interaction of the one we're changing is this interaction. So if we lower this, then it's coming down from the LUMO. So the HOMO of the modified dienophile is now further away from the LUMO of the diene. So that's not so good. On the other hand, the LUMO of the modified dienophile is now closer in energy to the HOMO of the diene. So this interaction is now smaller than that one, and so the reaction is accelerated. So this is a model for seeing why withdrawing groups, because they're taking the LUMO from here to here, is speeding up the overall reaction by making this gap dominant and this gap smaller than it would be from here to there. And if you think of a Lewis acid catalyst, all you're doing is actually meaning that this is a bigger contribution to the hybrid structure of the Lewis acid complex to the dienophile than it is than if there was no Lewis acid on the end. So effectively, you're lowering all of these by a little bit more, or quite a lot more. So you're making this gap even smaller. The result experimentally, as I say, is that a withdrawing group on the alkene brings everything down, and it makes the homodiene and the